Alright, this is my video 3 for the Game Engine Final Sprint. In this video, I'll be taking a look at the collision system, including the collidable groups, the volume B-spheres, as well as the visualizer, and the math and color tools. So starting off with the collidable, which the game object inherits from, we have a registration and deregistration command just like the other inherited types, but we also have a collision volume B-sphere and a model pointer which we store in here. The user has a get B-sphere function which can be used just to get a reference to the collision volume B-sphere. And then we also have the collision function itself, which is called whenever the collidable is colliding with something, which will return the type of collidable that you are returning or colliding with. Then we also have set collider model, which the user can call to set the model that the collision volume B-sphere is based on. So they'll set that in here, and then they can call update collision data with a world matrix, which if we check in this function, we'll just call compute data on the B-sphere, given the model and the world matrix, and then we will update the radius and the center of our collision B-sphere. And then we also have collision registration and collision deregistration functions, which are templated so that collision will work with any object class that the user creates that are game objects inheriting from collidable. So then we will create a new registration command that is a collision registration command of that templated type, and then we will submit that to the scene through the submit command, and then the registration will be handled by the scene registration broker. But if we look at the collision registration command itself, we'll see in here when execute is called by the scene registration broker that we will say collidable group of C register this collidable type, and the collidable group itself is a singleton. So if that collidable group already exists when we call register, we will just register to it. Otherwise, if this is the first of that collidable group type, then we will create a new collidable group. So then there will be one for each, say like each enemy or instance of a bullet. They will have their own collidable groups. But if we look at the collidable group itself, and here we can see that it is just a singleton that is templated, and then it just has a collection inside of it, which is the collidable collection, which when we register, we will add ourselves to that collection, and when you deregister, you will remove yourself. So this will be a list of all game objects of that type that are registered for collision. And then this down here is just for setting the singleton for null. This doesn't do anything, but then when in the delete, we can just clean up the instance and reset it back to null. But then we also have this function here to get the collider collection, which will return the list. So we will grab all collidables inside the list. And then the scene itself contains the collision manager, which is not a singleton. So upon creating the scene, we'll create a collision manager. And in the update function, second thing we will do is call process collisions. That's not what I want. I guess that works. We'll call process collisions in here, which will then run through all the collision test command bases and call execute, which all of those are added in the set collision pairs or set collision self, which are the collision test pair commands or the collision test self commands, which are set here through these user functions, set collision pair or set collision self, which the user does inside of the demo scene, which we can see here, where we set a collision pair of tank and enemy bullet and enemy. But then checking, so when we register that, we will create a new collision test pair command. which then the collision manager will call execute on. And when execute is called, it will grab the collection of collidables from the collidable group of one object and the collidable group of the other object. So in this instance, you could grab all of the bullets and then all of the enemies. And then for each one, we'll go through the list, grabbing their B-sphere, and then we will run a test with the Atlas math tools of intersect on B-sphere 1 and B-sphere 2. And if that's true, then there's collision, and we will call that in both game objects, or technically collidables. But this is our math tools, which is inside the tools filter, which just contains an intersect function for collision volume B-sphere A and B. And inside, it's just a wraparound to call intersect B and A and intersect B with A, and then we can return that test. That's true. Which this math actually is done inside the B-sphere itself. In here, we will take our center and then the other collision volume B-sphere center and our radius and their radius, and then we will return the math to determine whether or not they are overlapping, returning true if they are, false if they aren't. Which then all comes back here, and if that test result is true, then we're calling collision on both those collidables of that type. And then we also have the visualizer, which will use this color.h.cpp, which in the color.h we're just declaring all the different color types, and then in the CPP we're just setting the values for them, so that's all just the different colors that the user can access. Then up here we have the visualizer itself, which has a show B-sphere function as well as a visualize all, and then a render function. And the visualizer also has its own command broker, which is used for handling show B-sphere calls here. So this is a singleton, so you can call show B-sphere, which will create a new visualize command. And then we have this command list, which allows us to recycle commands, so we don't have to create more visualize commands than we need. So if there are not any more unused visualize commands, we'll create a new one. Otherwise, we'll grab the front of the list and then reset the values, and then we'll just add that to our command broker, which is simply the visualize all. We'll just come back and call command broker execute commands, which the execute commands in here we'll just call execute on all those command bases, which is just the visualize command, which we'll call visualize render here, which we'll just call this render function here, which just takes us to the private instance render function, which will then set the world, the color, and then call render. So this allows us to call show B-sphere outside of the draw function, because if we look inside of the Atlas, in the Atlas draw function at the top, we're calling the visualizer visualize all. So you can call show B-sphere anywhere, and the commands will be stored and then processed in the draw function of the engine so that they will draw no matter where you call them. I think that's everything, but if we're looking at something like a game object, like say the bullet, in the constructor we're just setting the collider model to be equal to the model that we're using for the bullet, and then when we're initializing we're always just calling update collision data on that B-sphere given our world matrix, And then in the scene entry, we're calling collision registration of the bullet, giving it this collidable type. And then in our update, we're always updating the collision data of our B-sphere to match the bullet since it's moving. And we're calling visualizer show B-sphere in the update with the color that is usually blue. And if we're getting collision with the enemy, then we're changing our color to red, and we're deleting the bullet with the submit exit. So then we'll always draw blue unless we collide with the enemy, then we will color ourselves red. And then similarly with the enemy bullet, we have a collision with tank where we're setting our collider model, updating the collision data, and registering ourselves for collision. And then when we collide with the tank, we'll color ourselves red and call submit exit, which will be scene exit, deregistering draw update, and collision deregistration. But if we watch this in engine, so we have a splash screen. You can launch into the game. You'll see the ships fire the bullets here. If we use freeze frame, you can inch the bullet forward until we have collision, where we see both the B-sphere for the bullet and the tank will turn red. And then since the bullet is calling submit exit upon collision, it will disappear in the next frame, like that. And you can also see if we fire at an enemy, an inch forward into collision, we'll see the bullet and the enemy B-sphere turn red, and both are set to call submit exit upon death, so we'll see both disappear in the next frame. And that is the collision system.